In this video, we're going to look a little further at the Pythagorean theorem and some other properties of right triangles that we can get. So just to start off, we're going to write down our Pythagorean theorem, which we know at this point is a squared plus b squared equals c squared. So basically, anytime we have two sides of a right triangle, we can always find that missing third side by using this. Now, you may recall that earlier this year, we looked at a picture and kind of introduced the Pythagorean theorem by playing around with different squares. The reason for that was because if we always look at the squares formed by the two smaller sides, they always add up to the same amount of the largest square from the largest side, the hypotenuse. So we can see that in this picture here in this GIF, but we're going to draw that on our own lesson here. So imagine that A, we would make roughly a square here. So remember, squares have all four sides congruent, and the area of this square would be the same as taking length times width or base times height, either way you're more comfortable calling it. But in this case, a squared would be our area for that square. Now, if I made another square down for B, it doesn't have to be perfect, just enough so you're getting the point out of it that we have B all the way around. The area of this square would be B squared this time, because the length and the width are B in this case. And finally, one final square is going to be formed with all matching sides of length C, giving that an area of C squared. While we've done something like that similar in the year, we now have new information that can help us show indefinitely why the Pythagorean theorem will always work. But first, we're going to revisit something we've done a little bit more recently. So in exercise number 2 here, we are going to have an altitude to a right triangle partitions it into two segments of lengths 3 and 9. So we know that that's going to happen from a right triangle. So I'm just going to get myself a rough sketch of a right triangle. It doesn't have to be perfect or drawn to scale. I also know that there's going to be an altitude drawn in, which is always from a vertex to the opposite side, making 90-degree angles. So we're dealing with 3 right triangles. And that segment, that altitude, is partitioning our hypotenuse into 2 segments of 3 and 9. Now, I don't have to draw it to scale or anything perfect like that. Anytime I make my own picture, it's open to interpretation. But because I have all the right triangles formed, the 2 proportions that we could use are hills or SAS. And we're going to think about which one's going to work a little bit nicer for us here. So if I read further, I'll figure out what I'm trying to find out is I'm looking for the length of the shorter side, or the shorter leg rather. So remember, the legs are the 2 sides of a right triangle that aren't the hypotenuse. So this is a potential leg and this is potential leg. But the shorter leg is going to have to be here. Not just because I drew it that way, but because it pairs up with the shorter partition piece here. So because of that, now that I know what I'm looking for, when I look at my 2 tests down here, my hills or SAS, I always ask myself with SAS, do I have anything on the altitude? Since there's nothing on the altitude, we will not use this proportion. We're going to use hills. And H stands for the hypotenuse of the big triangle. So that means we're going to start with 12 over the leg. And in this case, we'll look back. We called our leg this X value. We use that same piece twice. And that S is the segment along that split partition piece, and we want the one that's closer to the corresponding leg. So it's going to be 3 here. When we cross multiply this, we end up with X squared equal to 36. And when we go in and take the square root of both sides, X is equal to 6. So this means our shorter leg is going to be a length of 6. And if we wanted to, we can go in and find the larger leg, but we don't need to in this piece. We just want to remember how to set up the proportions. Now we'll have enough kind of throwback information to help us set up the proof of Pythagorean theorem here. So again, we have a right triangle, ABC, just like we just did. Like you'll notice ABC is that bigger outline. And then we have the altitude drawn to make two smaller triangles. So I'm going to first pinpoint those two smaller triangles that we have, and we're going to redraw them so that the orientation matches the original. So first we have this triangle here. The right angle's in the bottom left corner in our original. And if we look, A is across from that right angle. So A is going to be here in this case. Now D is going to be the part that's right here when we're looking at our sides of the triangles. I'm going to do this again now for the other triangle. The right angle is still going to be at that bottom left part. So that means across from that right angle was B. We're going to keep that here. And E is going to be the piece down here. And I'm just going to draw in one more triangle. I'm going to compare it to the original. You don't have to, but I just think it's nice to see that visual piece here. It doesn't have to be drawn to scale. We know that it was A, B, C originally. Okay, so those are our three right triangles now. So in this first part B here, set up a proportion involving the smaller right triangle, which we kind of gave that turquoise color, and the original. Write the proportion in product form. So I'm going to start with D over A equal to A over C, because I'm using the pieces that we have. And we know when we cross multiply, you're going to have A times A, which is A squared, and that's going to be equal to D times C. Over in C, we're going to do the same thing, but now we're doing the larger triangle and the original. So it's still talking about the original and that blue one that we highlighted. So same thing, but we're going to set it up as B over E equal to C over B. And the same thing's going to happen again. We're going to have B times B, which is B squared, equal to E times C. Now, because I know these two triangles are similar, I know all these proportions are going to map onto one another. I can use the additive property of equality to just set everything that I have equal to each other, but with the right corresponding pieces. So right now, what I do know here is that we have A squared is going to be, I'm going to add that with B squared, and it's going to be equal to its corresponding pieces, DC and EC. So equal to DC plus EC. Now we're getting a little bit closer to showing why A squared plus B squared equals C squared must be true. So when I do that, I want you to notice that there's something that they both have in common here. They both have C. So I'm just going to factor that C out back from Algebra 1, and I'm going to have D plus E in parentheses, and it's going to equal this whole first piece of A squared plus B squared. Now, our goal is to get this to be A squared plus B squared equals C squared. Let's look back to the top for a second. Isn't it true that C is made up of D and E in this case based off our picture? If that's true, it's like having C times C, which we know is C squared. So we've just shown that A squared plus B squared equals C squared. And just to take that one step further, we're going to redraw the original diagram using the new pieces we just did. So that original diagram before, remember, we know from what we did back here, we know we have A squared and B squared, but let's see how C squared's broken up a little bit here. So I know this side was A. So everything around here that's going to be a squared. I knew this piece is b, making this area b squared. But those pieces were equal to other things. Like b squared, if we looked up here when we set up that proportion, b squared was equal to e times c, just like a squared was also equal to d times c. So let's look at how that's formed. So we have d and e at these two locations, d and e. Area formula is the same, whether it's a square or a rectangle, whatever. So when I do this, I'm going to break this part up into being d times e. Okay, because we know a squared was equal, I meant the length of c. Because if we go back, actually, if I back that up to have the original picture that we did on the other page, I'm going to draw this in here to divide this up, because I know that this was a length of c. The whole thing's a length of c. But rectangles have opposite sides that are congruent. So this piece is c, and this is d here, and this is e here. This area here would be equal to e times c, which we know is equal to b squared. And this area here would be equal to d times c, which we saw was equal to a squared. So these areas are equal amounts, and they make up the full thing here, where this whole thing and this whole thing add up to the whole of Pythagorean theorem. Okay, so this is just another way to verify how do we know a squared plus b squared equals c squared each time. Now, you won't be asked to recreate this definitely on this test coming up, but it's just something nice to know and why Pythagorean theorem checks out. One final thing for today in this lesson is that special right triangles exist. With a right triangle that has the degrees 30, 60, and 90 always will be in a proportion that the smallest side, which is the side that is across from the 30 degrees since it's the smallest angle, is 1. The middle size across from 60 is radical 3, and the largest size, that hypotenuse, is 2. Okay, so it goes like 1, radical 3, and 2. Those are always in that proportion, while over here we have an isosceles triangle. Since we have 45 and 45, it's in a proportion of 1, 1, radical 2. So we can use those proportions when solving for the missing side that we want. Like in exercise 4 here, we're looking for how to find x. It's a 30, 60, 90 triangle. So that being said, one thing I can do is set up a proportion. So see how this piece is across from the 60? That would go with a radical 3 over x, while this piece across from 90 would go with 2 over 6. And when we cross multiply, we end up with 2x equal to 6 radical 3. And when I divide both sides by 2, we get x equal to 3 radical 3. And that's our missing side here. Same idea with b, only now we're using that other proportion from the isosceles, the 45, 45, 90. We have 1 and 7 go together, and radical 2 and x. So we're going to get x equal to 7 radical 2. Try C and D